And now we're going to talk about the concepts of chapter 3, which is titled Compounds Putting Particles Together. In chapter 1, we learned about the different elements that we have in the periodic table. In chapter 2, we learned that those elements are formed from putting together protons, neutrons, and electrons. And before we proceed into understanding these atoms more, let's just talk about all the history that had to come before all of these findings of the subatomic particles and the elements of the periodic table actually happened. So, let's understand that whenever we're talking about an element, elements are made out of atoms. And by definition, an atom is the smallest particle of an element that retains the characteristics of that element. As we can see in the picture in the top right corner, here we have an image of aluminum foil. Aluminum foil is made out of aluminum atoms. So each one of the spheres that we see here are going to be representing atoms of aluminum coming together to make that substance. Now, when it comes to the history of how we came to understand the electrons and the protons and the neutrons, understand that it all started around 400 to 300 BC with the Greek philosopher Democritus. So, during that time, Democritus proposed an atomic theory where he saw atoms as tiny, hard, and uncuttable. He didn't perform any experiments. All he saw is that, or proposed, I should say, that the different substances around him, like for example, water and fire, he proposed that those are going to be made out of these atoms that most likely, in his view, they had different shapes. So he proposed that, for example, water will be round because the way that it flows, but then fire will be spiky just because of the properties that it has. So at least it gave an insight on the idea that people started thinking about the substances that were around them. It wasn't until 2000 years later that John Dalton in 1803 experimentally illustrated that indeed the substances around us were made out of atoms. In the way that he described atoms were as solid, indivisible spheres. Again, these were all proposals, but at least he did the experimentation to demonstrate that atoms were in at that point just the smallest particle that where elements came from. And he further also proposed that these atoms could not be destroyed or reconstructed. After that, researchers, starting in 1897, started thinking, okay, is an atom it? Is that the smallest thing that we have of an element? And J.J. Thomson did what is called the cathode experiment. And in the cathode experiment, he was actually studying atoms and understanding, okay, is the smallest particle the atom, or does the atom have also little pieces incorporated there? Through the cathode ray experiment, he discovered that atoms indeed could be shaped like a sphere that have positive charge and contain a few negative charges. So J.J. Thomson was the actual scientist that discovered the existence of electrons. So he called it the plum pudding model because that is a popular dish where he's from. But if we try to relate it to something that may be more common in our area, it would be like a blueberry muffin, where the blueberries are going to be the electrons and then the cake is that area of positive charge. Now, in order to understand what was the content of that positive charge, then in 1909, Rutherford did the gold foil experiment. And in the gold foil experiment, he actually found that specifically atoms had divisible units composed of positive charges concentrated in the nucleus. So that was the major finding that he had, that the atom actually have a nucleus and the electrons were around it. Now, Rutherford did not discover the existence of protons and neutrons. That is attributed to other scientists, but at least with the gold foil experiment, he determined that atoms have a nucleus specifically. So by the time that we have the gold foil experiment, we didn't know if the electrons were free floating around the nucleus or they had specified positions on it. So Niels Bohr in 1913 proposed a theory based on the experiments that he was doing with hydrogen. So he actually designed mathematical equations to propose where the electrons will be located in an atom. And as you can see, he discovered with his experiments with hydrogen that electrons in atoms are restricted in certain circular orbits because he proposed in his model for the electron that lives in hydrogen that is going to be circling the nucleus similar to how planets circle the sun, and he called that orbits. Now those orbits, he viewed them as quantized energy levels. So mathematically, his equations work excellent for hydrogen, but it didn't work for the other elements. So then in 1926, Schrödinger just revamped the whole idea of the location of the electrons, introduced brand new mathematical equations, and he created what we called probability clouds. And these probability clouds that he designed are so good that is still the model that we use to date to understand the location of electrons. Now, he utilized the idea of these quantized energy levels that were first proposed by Bohr and is what we know now as periods. But the most important thing about Schrödinger is that these probability maps give you the location of electrons to a 90% certainty. And overall, these clouds of probability, if they're dense, then that means that you will find an electron in a high degree. But if they're less dense, then understand that there's going to be areas that we don't find electrons. Let's now see how these probability clouds that were created by Schrödinger actually look like. So understand that the shapes that you see right here are given by those probability cloud equations. And let's now give a name to those probability maps. We call them orbitals. So as you can see here, they are designated by a letter. So when it comes to an atom, these orbitals are going to live in the different periods of the periodic table. And again, that is what we know as the energy levels. So we can have electrons in an s orbital, which is the one that you see in the very top. You can have electrons in the p orbital, in a d orbital, in an f orbital. In the top right corner, you see that as a superscript, we have a specific value, and that's overall how many electrons maximum can be populated on each of these probability maps. Now, understand that when it comes to all of these concepts, all of that is incorporated into the periodic table. In section 3.1 in the textbook, we are going to now focus on electron arrangements and the octet rule to understand how those orbitals actually fit in to give us the locations of electrons. So first, let me introduce to you the idea of electron configurations. Electron configurations illustrate the distribution of electrons in the form of orbitals, and these orbitals are going to have a specific filling order. As you can see, this filling order is starting with energy level 1, there's an s orbital. Energy level 2, there's an s orbital. Energy level 2, there's a p orbital. Energy level 3, there's an s orbital. 3, there's a p orbital, so on and so forth. Now, you may wonder, why is it that they're not going in order? Well, because energetically in the laboratory, it was determined that this is how the electrons populates those different levels, meaning if you use an analogy, it's kind of like having different floors in a building, and within the first floor, you only have like a room in the bottom. And as you build to the second level, you have at second level two different types of room, like an S and a P. and so on and so forth. Now, in the periodic table, all of this information has been incorporated. So for the purposes of electron configuration, understand that helium, I'm going to place it right here next to hydrogen so it looks more even. I'm just going to just take it away from this corner and place it next to hydrogen so it makes a little bit more sense. Now, we can see that in the periodic table, this is how it actually looks like. In the periodic table, the first two groups, that's where we mainly have the idea that the s orbitals live there. In the middle of the periodic table that you can see in the color peach, that's where the d orbitals live. In the last six groups, that's where the p orbital electrons live. And understand that when it comes to this, the main thing that I want you guys to know, oh, and I forgot, the f orbitals are in the bottom, but we typically don't talk about them because those electron configurations get to be more complex. In this course, S, D, and P is what mainly we're going to focus. Now, when it comes to what do I need to know in terms of electron configurations? If you are given an electron configuration, I want you guys to know, how do I determine which element I'm talking about and the symbol of the element? And later we're going to explore how the electron configurations can also tell us about the electrons that are in the outermost shell, which are very important to explain the behaviors and the properties of elements when they're making compounds. So let's explore now how, if I'm given an electron configuration, I can figure out which element I'm talking about. And as you can see here, we have a series of electron configurations and we need to find out which element we have. So I'm going to use number 1 to explain what the electron configuration is actually trying to tell us. In an electron configuration, this value that I'm highlighting in yellow tells you the energy level. In other words, the period of the periodic table that we're talking about. So this is energy level for an electron, but also corresponds to the period that we are talking about. The letters that I'm highlighting in magenta, those are going to be the orbitals themselves, S versus P. Lastly, in green, I'm highlighting these digits. And these digits, let me use a different color, that I'm circling in orange are going to be the electrons in an atom. So if I'm given the electron configuration, how do I know which element we're talking about? Well, you're going to take those digits that are in the superscript and you're going to add them. So you're going to say 2 plus 2 plus 1. That equals 5. So the atom that I'm talking about has 5 electrons. Because so far we are speaking specifically of atoms that are in ground state, this is going to equal the atomic number. So I'm looking for the element that has atomic number 5. And when we look at the periodic table, that corresponds to the symbol that is a letter B, and B corresponds to the element that is called boron. Let's do also example 2 so we can follow the information. So if I'm giving an electron configuration, what I'm going to focus on is these digits, the superscripts. And I'm going to say 2 plus 2 plus 6 plus 2 plus 2 . When I add all these numbers, this is 14 electrons in this electron configuration. Because that equals the atomic number, I'm going to look at something of atomic number 14. So atomic number 14 that equals the element that has symbol Si, and the name for Si is silicon. So make sure that you practice with the other problems that we have there. So now that we know if we're given an electron configuration, how to determine the elements, let's explore other things that we can find out from that electron configuration. Because as I mentioned, there is important information given in those electron configuration. Now, there is the whole idea of valence electrons. And as you can see by definition, a valence electron is going to be the number of electrons in the outermost energy level for an element. So if I look at my electron configuration, okay, if I look at the second problem, what is that outermost shell? Well, specifically what I'm paying attention to is these large digits, and I'm comparing 1 versus 2 versus 3. So if something is in the outermost shell, that means that it's going to be the largest of those digits that represent the energy level of or the period. So as you can see, for this example, the largest value that I have is number 3. So I'm going to circle all of the orbitals that I have at level 3. And as you can see, I have S and P, and each of them have 2 electrons. So at first you can say, oh, okay, so I see that in silicon at level 3, specifically, I have 2 electrons in the S orbital, and I have 2 electrons in the P orbital. Now, that correlates to say, well, how many total are going to be in this level 3? Well, we're going to say, well, since we have 2 in the S plus 2 in the P, that means that silicon has 4 valence electrons. Now, there is an easier way to do this, specifically because silicon is a representative element. 4 elements that are representative elements, their group number will tell you how many valence electrons they have. And as you can see here, if you're in group 1A, 1 valence electrons. If you're in 2A, 2 valence electrons. As you can see, there's a trend up to 8A, 8 valence electrons. Now, if we look closely at the periodic table, silicon is actually in group 4A. So the result that we saw previously makes sense because, oh, silicon is in 4A. It has 4 valence electrons. And then we see here that where do those 4 valence electrons live? Oh, 2 in the 3s orbital and 2 in the 3p orbital. So I just wanted to illustrate how that is actually obtained. Now, understand that there's an exception to the rule, and I'm just going to write it here in the bottom. In 8A, we have helium. Helium doesn't have 8 valence electrons. It only has 2 valence electrons. So that's the only member of group 8A that the rule doesn't apply to. Now, these valence electrons can also be illustrated by writing dots around the element. As you can see here, we have aluminum. Aluminum is in group 3A. And as we saw the trend previously, that means that it has 3 valence electrons. And we represent them by the 3 dots. So, for example, for silicon, if we're trying to do its Lewis dot structure, we're going to do the symbol Si, and then we're going to do 1, 2, 3, 4 dots around it, and that's how we illustrate the valence electrons. Now, why is all of this idea important? Because when it comes to the stability of an atom, most atoms want to reach what is known a noble gas configuration. Noble gases are very special elements in the periodic table. All of the noble gases have full valence shells in them. And remember, if we think about it, that full valence shell, because the atoms want to reach being a noble gas configuration, then that's what they want to obtain, 8 electrons in their outermost shell. Now, remember that neon, as you can see, is the only member of 8A that doesn't have 2 valence electrons. So having that stability or having that property of full valence shell is the reason why noble gases are so non-reactive. So as an atom, in order to reach that stability, you want to get to a place where you're not going to be as reactive. So let's first discuss what is a noble gas configuration when it's written and derived from a full electron configuration. So when we talk about noble gas configurations in terms of a full electron configuration, as you can see here, we have 2 atoms, neon on the left, sodium on the right. So when it comes to this concept, understand that the electron configuration for neon is 1s2, 2s2, 2p6. The electron configuration, the full one for sodium, is 1s2, 2s2, 2p6, 3s1. Because all of this looks like neon, when we're writing the noble gas configuration, then that 1s2, 2s2, 2p6 can be replaced by putting neon in brackets and representing, hey, this portion of sodium is looking like a noble gas. It's not that sodium turned into neon. It's just that those electrons look like the position where neon has them. Then after that, we're going to put what is the other electrons that are outside. So what are these electrons representing? The valence electrons, the ones that are in the outermost shell. Remember, the group number tells you the valence electrons. Sodium lives in 1A. That means it has 1 valence electron. And where does that valence electron live? Look, in the 3s1.